Hello, everyone. Welcome to today's live broadcast, High Pressure Capillary IC for Food and Beverage Analysis. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LCGC North America and sponsored by Thermo Fisher Scientific, a world leader in serving science. Thermo Scientific provides analytical technologies, reagents, consumables, services, and software for cutting-edge scientific research to routine industrial applications. This web seminar is part of an educational series to provide solutions for pressing application challenges. We have a few important announcements before we begin. This webcast is designed to be interactive, so we encourage you to ask questions during the event. You can type your questions in the Submit Question box located below the presentation window, and we'll answer as many questions as we can during today's live event. You can also enlarge the slide window at any time by clicking the Enlarge Slides button, also below the presentations window, and the slides will advance automatically during the event. And lastly, if you have any technical problems viewing or hearing the presentation, just click the Help button, also below the presentations window. I would now like to introduce today's speaker. Joining us today is Terry Christensen, who has been an applications chemist at Thermo Fisher Scientific for 8 years, developing and promoting applications to support new product introductions across all markets needing ionic determinations. Prior to joining Thermo Fisher Scientific, Terry spent 18 years in the electronics industry as a Dionex customer, applying her experience in trace analysis, material science, and analytical instrumentation, and leading laboratory groups and project teams to solve electromigration, corrosion, and contamination issues. Before working in the electronics industry, Terry applied her bachelor's degrees in chemistry and biology from the California State University, Fresno, across diverse industries. Terry, thank you for joining us today. Why don't you go ahead and get us started?
Thank you, Laura. Today in my presentation, I will be discussing the importance of IC analysis to the food and beverage industry, the values of capillary IC walk-up system, and the Thermo Scientific Dionex ICS 5000 HPIC system, the benefits of high-pressure capillary IC, high-resolution, smaller particle size, the 4-micron columns, and finally my results and summary. The importance of IC to food and beverage industries. Beverages are complex matrices containing organic acids, inorganic anions and cations, preservatives, flavor additives, and sugars or sugar substitutes. The determination of these analytes are important to the beverage industry to verify content needed for labeling and formulations, assess product freshness, protect immune-compromised and health-sensitive consumers, identify accidental contamination, and identify adulteration to illegally increase profits. IC is also used to monitor and control processes and develop new formulations. Inorganic anions and organic acids are monitored to maintain product quality, control manufacturing, and to develop new formulations. Additives are intentionally introduced to achieve product stability or flavor. Acidulants are additives such as phosphoric acid and citric acid used to maintain acidity, reduce pH, and minimize biological growth. Flavoring are often organic acid additives added, such as citrate and malate. Flavor boosters are organic acids that are very similar to the natural organic acids found in the product. Preservatives are additives added to minimize biological growth. Sugars or sweeteners are added to increase sweetness to a desired formulation. And carbonation is added to enhance flavor and to minimize biological growth. IC is also needed to meet regulatory labeling requirements. In the U.S. and in many other countries, manufacturers are required to report the contents and concentrations to meet regulatory labeling requirements. The ultimate purpose of this regulation is to protect the consumer, especially the immune or health-compromised consumer, and to use product labeling as a means to prevent products being falsely advertised. Therefore, the manufacturers are required to measure and report concentrations of inorganic ions, concentrations of vitamins and trace metals, types of juice, percentage of juice types, and additives. IC is also used to identify the fruit and the seed characteristics and to determine ripeness. Organic acids are also naturally occurring. Many of these same organic acids used as additives are naturally occurring in the original plant or fruit. Organic acids are characteristic of the fruit or plant source. IC is used to profile the fruit or seed source. It has been rumored that some industry experts can use profiling to tell even where the crop was grown. IC also monitors organic acids as indicators of fruit and seed ripeness. IC is also used to identify and monitor fermentation byproducts, both intentional and unintentional fermentation byproducts. Intentional byproducts are used by the food processes to encourage fermentation to enhance and create flavor. The most common examples, of course, are beer, wine, and cheese, and it's believed that these may have launched our civilizations. Other less known fermentation uses are in the coffee and chocolate processing. Unintentional fermentation is by microorganisms such as bacteria, yeast, or fungi that generate undesirable metabolic byproducts. Most common ones are acetate and lactate. Another less known metabolic byproduct is acetaldehyde, which is a metabolic byproduct found in wine believed to cause hangovers. IC is needed to identify accidental contaminants introduced inadvertently, typically by contaminated soil or water. These are typically heavy metals such as lead or mercury. Accidental contamination is also as a result of a breakdown in the manufacturing process or any time during the transport of the product, before as a raw material or after it's been processed. Adulteration, which is intentional contamination, is always done to increase profits. This area has been a hot issue in the past and unfortunately will continue to be very important in the future. Adulteration is all about money and increasing profits. There are different reasons for adulteration. The most common one is when a lower cost product is illegally added to a higher cost or more desirable beverage to increase profits. The most common example is apple juice and orange juice. The classic example for adulteration is apple juice and orange juice. Historically, apple juice was plentiful and therefore cheap, and orange juice was less available and therefore more expensive. Some dishonest people decided to make more money by diluting the orange juice with apple juice and selling it at the orange juice price. Now, with the health benefits of pomegranate juice in the news and cranberry juice, the temptation is to dilute pomegranate or cranberry juice with grape juice and sell it as 100% pomegranate or grape or cranberry juice. Another type of adulteration that is more subtle, I consider it like an over-marketing type of adulteration. When a small amount of a product with a perceived health effect is added to a beverage, thereby making the product more marketable, more desirable to buy. However, the small amount of the product actually has no health effect. To analyze these samples, we will use capillary IC. As a reminder, capillary IC is ion exchange separations at microliter per minute flow rates on a 0.4 millimeter ID columns and detected by suppressed conductivity using the capillary electrolytic suppressor designed for capillary IC. Let's review some of the major values of capillary IC. IC on demand, permanent availability of the system. According to our customers, this is the top value for capillary IC. They find lots of benefits in a true walk-up system, no waiting for equilibration, less calibration, and quicker results. Eluent generation, precise and accurate electrolytic generation in line. Just add water. Higher mass sensitivity. The ability to use less sample and still achieve high sensitivity. We take full advantage of this in our 2D IC applications. Lower cost of ownership, less eluent, less waste, and longer life on our EG cartridges. As Capillary IC has been on the market for a few years now, we have been able to validate some of these top customer values for Cap IC. As you know, the Dionex ICS 5000 is the world's first capillary IC. Now we are introducing another world's first, high-pressure capillary IC. 5,000 psi may not sound like a lot in the world of HPLC, but when you consider that the ICS 5000 is a 100% plastic system, this is quite an achievement. With the ICS 5000 capillary IC, we have a high-pressure system capable for capillary IC. Continuous operation up to 5,000 psi when configured as a reagent-free system. This results in increased productivity with fast runtimes, improved separations, and higher resolution with small particle columns. RFIC IC by electrolytic generation. In reagent-free IC, the eluent is electrolytically generated in line. Just add water. The eluent generated is based on the equation where the KOH concentration is proportional to the current over the flow rate. In the eluent generation cartridge, as the water enters into the hydroxide generation chamber, DC voltage is applied to provide a constant current between the platinum anode and cathode, resulting in a precise amount of hydroxide generated at the cathode. The potassium cations migrate across the cation exchange membrane, combining into a precise and reproducible concentration of potassium hydroxide eluent. With RFIC, high-purity contaminant-free acid or base eluents are generated in line precisely and reproducibly for isocratic or gradient separations. No longer do you have to prepare eluent because only water touches the pump. It also minimizes pump maintenance. RFIC minimizes the ease of use, saves time and labor normally spent on eluent preparation, and eliminates person-to-person variability and eluent preparation errors. Suppression. The detection method with RFIC is suppressed conductivity detection. Suppression is the technology that enabled modern IC. Without suppression, the conductivity detector sees weak signals from potassium salts of fluoride, chloride, and sulfate in the presence of a strong background signal from potassium hydroxide eluent. With suppression, potassium ions in the eluent stream are replaced with hydronium ions, so the detector now sees highly conductive acids of the anions, hydrofluoric acid, hydrochloric acid, and sulfuric acid, in the presence of a weakly conductive eluent, hydronium hydroxide, which is water. Suppression increases analyte signals while reducing background signals, yielding much more sensitive and selective detection of ions. We are now introducing the 4-micron particle capillary IC columns. These columns provide improved resolution and provide faster runs and better results. The benefits of ion exchange columns with 4-micron particle size is smaller particles provide better performance, faster runs with higher flow rates using the 150 millimeter columns, high resolution with standard flow rates using 250 millimeter columns. And here we show 3 applications for our 3 new 4-micron capillary IC columns. Anions in environmental waters on the Dionex IonPac AS18 4-micron column, organic acids in foods and beverages on the Dionex IonPac AS11 HC 4-micron column, and amines in chemical process solutions on the IonPac CS19 4-micron column. Here is what is possible with high-pressure capillary IC and 4-micron high-resolution small particle columns. These peaks are so narrow, they are reminiscent of GC peaks. The efficiencies are typically 10,000 to 15,000 plates. Here we demonstrate the improvement in resolution using the smaller 4-micron particle resins. On the top chromatogram is the 4-micron particle column. On the bottom chromatogram is the 7.5 micron particle column. It's the same chemistry column and the same standard injected on both columns. As you can see, there is much higher resolution and more narrow peaks in the 4-micron column. Lactate, acetate, valerate, monochloroacetate, bromide nitrate, malate sulfate are critical peak pairs that are highlighted in blue. As you can see, these columns show improved resolution on the 4-micron column. Generally, reducing particle size does increase the column pressure, as in this case. To achieve these separations, we must use an IC system capable of running at higher pressures, such as the Dionex ICS 5000 HPIC capillary system. Fast IC columns facilitate 2 times faster separations. The standard 250 millimeter long columns often have higher resolution than necessary to separate analytes of interest. For example, common anions. The shorter 150 millimeter columns, using the same chemistry as the standard columns, accelerate separations while still providing sufficient resolution for many analytes. Using these faster columns increases throughput with fast columns by a factor of 2 times, increases productivity, and delivers results faster for rush samples. Here we show that faster run times without sacrificing resolution. On this column, the AS18 4-micron particle size column, we show flow rates from 10 microliters to 30 microliters, with the system back pressure increasing from 1140 to 2820. Here we show the separation of 7 inorganic ions using a 4-micron particle column at different flow rates from 10 microliter per minute to 30 microliter per minute, with the system back pressure increasing from 1140 to 2820. The high-pressure ion chromatography system allows the use of high pressure for running higher flow rates with the 4-micron columns. This column is designed to have a low system back pressure for fast separations of water samples. The column is designed for fast separations of samples with simple matrices, such as bottled and drinking water and wastewater samples. A typical bottled water sample contains chloride and sulfate, and sometimes carbonate and citrate, where a citrate peak will elute after the phosphate peak, which is peak number 7. This provides faster run times without sacrificing resolution. Fast, high-pressure separations of a 7 anion standard. This slide demonstrates fast separations on a different chemistry column called the Dionex IonSwift Max 100. It's a monolith column with IonPac AS19 chemistry. This application is a better example demonstrating the advantages of high-pressure capillary IC. The high-pressure capillary IC system operates at a system pressure up to 5,000 psi. This higher system pressure capability allows faster speeds previously impossible on the capillary IC system. Here we demonstrate anion determinations using a 7 anion standard with increasing capillary flow rates from 12 to 24 microliters per minute on the IonSwift Max 100 capillary size monolith and exchange column. The IonSwift Max 100 optimized with the Dionex IonPac AS19 chemistry is a high efficiency, fast flow rate column resulting in 7 anions determined in 9 minutes at 25 microliters per minute with a 3,900 psi system back pressure. Here's our first example using capillary HPIC to monitor a formulated beverage. High-pressure IC is used to decrease run times while maintaining baseline resolution. The flow rate is increased 2.5 times with the system back pressure well within the 5,000 psi limit. Citrate and phosphate, highlighted in blue, are important acidulants and preservatives in the carbonated cola beverages, and therefore are important to the beverage industry. Citrate is also commonly used as a flavor enhancer in unexpected areas. For example, citrate is added to some cheaper brands of bottled water to make it taste better. Here we are comparing the separation of anions in a fruit-flavored beverage by using HPIC to elute 8 peaks within 10 minutes. This further demonstrates the use of organic acid determinations to maintain beverage quality, maintain beverage acidity, and thereby prevent product spoilage. In this formulated beverage, benzoate, highlighted in blue, is added as a preservative. Carbonate and phosphate, as phosphoric acid, are added as acidulants and provide a desired flavor. Malate and quinate are added to provide a tartness and a fruit flavor. This example, young coconut juice and young coconut flavored beverage, was created prior to my HPIC system. I included this example to show the importance of product labeling and perhaps an over-marketing example. Here we compare juice from a young coconut on chromatogram A, popularly perceived as providing health benefits, and a carbonated beverage with a young coconut flavoring, chromatogram B. Young coconut juice is promoted as providing many health benefits, most of which are not fully confirmed. However, in some parts of the world, young coconut juice has been used as a saline substitute because of its high salt content and because it's considered relatively sterile as it's sealed from the outside world. Young coconut juice in chromatogram A has high amounts of malate, labeled in blue, and salt, chloride, sulfate, and phosphate, which gives it an unpleasant taste. The flavored coconut beverage in chromatogram B contains very little of the components in the original young coconut juice. However, citrate has been added as an acidulant in red. At this concentration, it is unlikely that the juice in the carbonated beverage would have any effect on improving health, but it does make a tasty, refreshing drink. Apple and orange juice. These chromatograms demonstrate high resolution using the high-pressure capillary IC and the high-resolution column IonSwift Max 100, and the classic example of adulteration. Historically, orange juice was less available and more expensive than apple juice. Some not-so-honest people decided to improve their profits by diluting the expensive orange juice with cheaper apple juice and selling it as 100% orange juice. Apple juice is shown in chromatogram A and orange juice in chromatogram B. Notice that the orange juice has a higher chloride content, highlighted in green, malate, oxalate, and citrate, highlighted in blue, whereas apple juice is mostly malate with very little other organic acids. The high citrate in the orange juice provides that tart flavor, acid flavor associated with orange juice, whereas the malate alone provides that sweeter, smoother flavor associated with apple juice. Here the organic acids are natural components from the fruit. These differences in organic acids can be used to profile the illegal adulteration of orange juice by apple juice. The product labeling requires the listing of fruit juices and percentages, thereby requiring organic acid determinations. Currently, with the health benefits of pomegranate juice espoused in the news, the adulteration is now more likely to be grape juice illegally added to pomegranate and sold as 100% pomegranate. Brewed, caffeinated, and decaffeinated coffee. This is also another low-pressure separation as another example for a common adulteration case. Here we compare brewed caffeinated coffee, chromatogram A, and decaffeinated coffee, B. Coffea arabica is a more desired and less abundant than the cheaper, lower-cost Coffea canephora variant Robusta. Therefore, Robusta is more commonly used in decaffeinated coffee or legally blended into Arabica to make cheaper blends of coffee. In chromatogram B, the decaffeinated coffee also has lower quinate concentrations, which is characteristic of the Robusta coffee, whereas quinate in blue, peak 1, is higher in the caffeinated Arabica coffee as expected. Quinate, lactate, acetate, propionate, malate, succinate, butyrate, citrate, glutarate, fumarate, all in blue, are fermentation byproducts from the wet processing of the coffee fruit prior to roasting. The caffeinated sample has higher concentrations of butyrate, glutarate, and malate succinate in red, which could attribute to the higher flavor associated with Arabica coffee. Cranberry and apple juice. Here we show our first application on the Dionex IonPac AS11HC 4-micron columns. Cranberry is another expensive juice and subject to illegal adulteration. Here we compare apple juice and cranberry juice on the high-resolution IonPac AS11HC 4-micron column using a gradient separation by high-pressure ion chromatography. These separations exemplify the resolution possible combining high-pressure ion chromatography with 4-micron columns. The system pressure approaches 4,000 psi, but this is well within the operating limits of the Capillary ICS 5000 HPIC system. In this separation, methanol at 10% was added to the water to increase the resolution of some critical pairs of peaks, such as succinate malate, fumarate, and oxalate, highlighted in blue. Cranberry has the characteristically high concentrations of quinate, succinate, and citrate in blue. Succinate gives it its characteristic bite. Unintended fermentation in orange juice. Here we have an example of an unintended fermentation sample. A diluted orange juice sample is separated with a gradient eluent from 1 to 60 millimolar KOH on the Capillary Dionex IonPac AS11HC 4-micron column on a high-pressure IC. The peaks are amazingly narrow, characteristic of this column, and demonstrating the advantage of a smaller particle column. Pressure of this column is again around 4,000 psi and is only possible using a high-pressure capillary IC system such as ICS 5000 HPIC system. What is also interesting about this sample are peaks 3, 4, and 9, which are lactate, acetate, pyruvate, and malate succinate in blue. Peak 14 is also suspect, and it might be oxaloacetate. These are fermentation products from biological activity, evidence that the juice is spoiled. Here's a more common example of fermentation. A diluted white wine sample is separated with a gradient eluent from 1 to 60 millimolar KOH on the Capillary IonPac AS11HC 4-micron column. The peaks are again amazingly narrow, characteristic of the column, and demonstrating the advantages of the smaller particle column. Again, the pressure on this column is around 3,600 psi, which requires the high-pressure capillary IC system, such as the ICS 5000 IC. Some amounts of lactate and acetate are present, hopefully not a problem for this wine. The other organic acids from fermentation provide the characteristic flavor of this wine: malate, succinate, tartrate, and fumarate in blue. And in my final application, I have 3 beer samples more fermentation products, separated again on the IonPac AS11HC 4-micron capillary column with a gradient separation. Please notice the small carbonate peak, number 8, in all of the beers. So beer lovers, don't despair. These samples were degassed prior to injection with the final amount removed with the aid of the capillary carbonate removal device, the CRD. Beer is a plant product, and therefore the sulfate and chloride concentrations are high, labeled in green. But sulfate and chloride are critical in mash filtration, and high concentrations reduce the hop extraction, reducing the bitterness provided from the hop. Lactate, acetate, and pyruvate, fumarate, succinate, and malate are all fermentation products and expected to be in beer in blue. In these samples, there are differences in phosphate, which is in pink, citrate and pyruvate in blue, that could be used to profile the beer for product quality or product characteristics. Beer sample number 1 in black is pretty interesting. I noticed that it has higher concentrations of phosphate and citrate. Seems unlikely that citrate was added for citrus flavoring, however. Citrate is also a chelating compound, and it will affect the pH. Phosphate is present as a pH modifier in mashing and during hot boil, and it has a clarifying effect on the beer. We could speculate that beer 1 has higher mash and hops than the others, or it needs more phosphate to control pH in the presence of citrate. Or maybe beer 1 has an intentionally higher metal content in its formulation and therefore needs more chelation and higher phosphate to maintain pH in the presence of citrate. So in conclusion, inorganic anion and organic acid determinations by ion chromatography are needed to minimize adulteration and provide safe, consumer-friendly products, determine product freshness and appropriate fermentation, meet product labeling requirements, and monitor product formulation. Capillary, high-pressure ion chromatography provides many advantages, including high-performance separations with higher response, narrower peaks, and increased resolution using the smaller particle columns. They also provide higher flow rates resulting in shorter runtime, thereby increasing sample throughput. Capillary on-demand IC is always available for sample analysis, reducing cost of ownership and minimizing waste to 5 liters per year.
Thank you, Terry, for that informative presentation. Before we get started with the question and answer session, I just would like to remind the audience how to submit questions. You can do that by typing your questions in the small text box, which is located in the lower left-hand side of your screen, and then click the Submit button. And we will answer as many questions as we can in the time that we have. So now let's pull up our first question. Terry, are all Dionex columns going to be available in the capillary format?
Most of them. We have already 20 capillary columns available. We plan to have most of our columns in capillary format except many of our older columns.
Great. And how many you might have just answered this, but how many 4-micron columns are available currently?
Currently we have 3 4-micron columns available in capillary format. That's the IonPac AS18 4-micron, the IonPac CS19 4-micron, and the IonPac AS11HC 4-micron.
Great. Here's another question. What kind of injection volumes are you using for these analyses?
These are all capillary format columns, so the injection volume is 0.4 microliters.
Great. Let's see. Let me find another question here. Slide 25 mentions the recycle mode. Can you explain how that is used?
That's our suppressor. As the eluent leaves the conductivity detector, it enters back into the suppressor on the regen line, and thereby flushing helping the suppressor reduce the baseline and increase the peak response.
Great. Let me pull up another question here. What size particles are used in the older Dionex columns?
Most of our particle sizes, most of our columns have 7.5 micrometer particle sizes. Some of the columns, though, like the AS15, have already been converted to smaller particles, such as 5 micron. But most of them, if you look at, are 7.5 micrometer.
Excellent. Here we go. I'm trying to read this question here. Have you done any cation applications in food and natural products, such as NH4 in tobacco and food?
NH4 in tobacco and food. We have not. It is on my list of fun things to work on next. I think some of my colleagues have done some work in Europe on tobacco, and the tobacco applications are on our list.
Great. Yes, I noticed a lot of the applications you talked about here today were in beverages.
Yes.
Was there a specific reason for that, or was that just the examples that you provided today?
I like beverages, so I can go to the grocery store and buy all the samples I want. But there's been a lot of interest in tobacco analysis, especially in our EU and the U.S. area. The FDA is planning on adding monitoring of tobacco for lots of particles.
Yes, you're right.
So
the legislation and the regulations are coming forward soon, I think, from the FDA, now that the FDA in the U.S. is starting to monitor tobacco products.
Yes, they have a list of 93 contaminants that we'll be looking at. They'll be covering all types of analytical techniques from GC to IC.
Excellent. Yes, and I'm sorry, I'm just trying to refresh my questions here and see what other questions have come through. But yes, I do understand that there's going to be a lot of analysis coming out of the new tobacco regulations. So a lot of folks will be doing a lot of new analysis that they didn't necessarily have to do before for regulatory reasons. Very good. I'm just seeing if any new questions have come in. I think I got all the questions answered, so I think we'll just wrap up then today. Terry, thank you so much for answering those questions and for your excellent presentation.
Thank you. It was my pleasure.
Great, thank you. I'd also like to thank everyone in the audience for participating in today's event. And I would like to thank our sponsor, Thermo Fisher Scientific, for making today's webcast possible. This webcast will be available for on-demand viewing through May of next year, and you will receive an email from LCGC North America alerting you when the webcast is available for replay. We invite you to send that announcement to your colleagues who may have missed today's live event. We look forward to seeing you all next time. Goodbye.